Hello everyone. The title of this video is Evaluating Exponential Functions. The examples I'm going to be doing in this video are taken directly from a free online textbook at openstacks.org, and I'm in their Algebra and Trigonometry text, section 6.1, called Exponential Functions, and I'm under the heading Evaluating Exponential Functions. And each example I'm going to do is either going to be an example taken from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Alright, so this is simply about evaluating a function, plugging in inputs and getting outputs. So let's just get into it. Alright. So in the first examples I have for you, we're just simply asked to find the requested value of each function and round to 4 decimal places, which would be the nearest 10,000th if necessary. Alright, so each of these is going to be an exponential function, meaning that your base is going to be you're going to have a base and an exponent involved. The base will be some positive real number that's not 1. And the exponent will have a variable to the first power in it, right? An x in it somewhere, or a t or whatever. Alright, so here we have f of x equals 5 times, and then your base and exponent 3 to the x plus 1 power. And we're simply asked to evaluate, what is the value of this function when the input is 2. So f of 2 is 5 times, and then 3 to the 2 plus 1 power. Simplifying that power, that's 3 to the third, right? 5 times 3 to the third power. Now remember, 3 to the third is 3 times 3 times 3. That's 27. So we have 5 times 27, and that's 135, right, which doesn't need to be rounded. It said if necessary. This doesn't need to be rounded to 4 decimal places, right? And that's it. That is all I'm going to be doing in this video. This should be a very simple video, in my opinion. Simple topic. So 135, and this also means that if you were to graph this function, the ordered pair 2, 135, that point would be on the graph. Wonderful. So let's keep this up. So here we have another one where, again, there's going to be some base and exponent involved, where the base is a positive number that's not 1, and the exponent has a variable to the first power in it, right? Like this x minus 5 here. Okay. So we have f of x equals 8 times 1.2 to the x minus 5 power. And we're asked to evaluate the function when the input is 3. So simple enough. F of 3 is 8 times 1.2 to the 3 minus 5 power. Now 3 minus 5 is negative 2. So 8 times 1.2 to the negative 2 power, and this, since there's the decimal here, I'm just going to go and enter this in a calculator, and I'll just go to that Desmos site, free online graphing calculator, desmos.com. And then off to the side here, we can just enter the calculation we're making. 8 times 1.2 raised to the negative 2 power, and we're seeing 5.5555. It looks like 5 and 5/9. All right, probably something I could have calculated by hand, but still. And if you round this to the nearest 10,000th, right, to 4 decimal places, you see the 5th decimal place is a 5, meaning I would bump the 4th decimal place up 1. So this would round to 5.5556 if I was rounding to 4 decimal places as they're asking. So it's approximately 5.5556. There you go. That's all they want. Right? Input 3, output, a little more than 5.5. That's it. And again, that's all I'm really doing for this video. Okay. Here we have f of x equals 2 times 5 to the x. Again, you see a part in here where you have a numerical base with a positive number base that's not 1, and an exponent with a variable that's to the first power, just x here, and then it's times 2. And what's the value of f at negative 3? So f of negative 3 is 2 times 5 to the negative 3rd power. Right. Now I can do this one by hand. I don't need a calculator for this. This is 2. Now remember, 5 to the negative 3 is 1 over 5 to the positive 3, right? Remember that negative powers are just the reciprocals of positive powers. And 5 to the positive 3, 5 times 5 times 5 is 125. So this is 2 125ths. And I can get this to decimal form pretty easily by multiplying the numerator and denominator by 8. You'll see why in a second, right? Because 8 times 125 is 1,000, a power of 10. Right? So this is 16 in the numerator, divided by 1,000 now in the denominator. Remember, when you divide by powers of 10, that moves the decimal point to the left. It will move to the left 3 places. So this is 0.016, or 16 thousandths, right, as a decimal. And that doesn't need to be rounded to 4 decimal places because it's just a bunch of zeros after that. There we go. So input negative 3, output 0.016, 16 thousandths. Okay. All right. Now the next two examples have some sort of constant added on to the the basic exponential function. So here we have f of x equals, it's an exponential. You have some number, times positive base to a variable power, right? There's an exponential. This plus 1.5 afterwards, right? If you just add or add a constant, plus 1.5, minus 3, whatever, it just moves the function up or down, right? Let me just show you, remind you of a transformation in the Desmos site. So yeah, so I'll put in that initial term, right? Y equals, we had 2.7 times, and then base 4 raised to the power of negative x plus 1. Oops, that plus 1 should be in the exponent. Put that in parentheses then. Okay, so that's all in the exponent. And you see it's an exponential function, right? You got the domain is all real numbers. The range is all positive numbers. You have a horizontal asymptote as the x-axis. But then throw on that plus 1.5, and you see all it did was move the graph up 1.5 units. So instead of the horizontal asymptote being the x-axis, now the horizontal asymptote is the line y equals 1.5. And I'll make that like a dashed line. And you can see as the graph, as you move to the right here, the graph is going to approach. It looks like it's touching it right now, but it actually isn't. It's actually all above. If you zoom in close enough, which I will here, if you zoom in close enough, you'll eventually see the green graph doesn't actually touch the purple dashed line. I had to zoom in pretty far there, but y equals 1.5 is now the horizontal asymptote as opposed to the x-axis, y equals 0. Again, the whole reason for that move is because you move the entire graph up 1.5 units with this plus a constant at the end. And I'm hoping you remember your function transformations, right? Just adding a constant at the end moves a graph up or down so many units. All right, and then we're asked to plug in -2 to this function. So I'll do that. What's f of -2? Well, this would be 2.7 times 4 to the third power, because it would be the opposite of -2 and then plus 1. All right, it's -x plus 1. And then you got the plus 1.5 at the end, plus 1.5. So we have 2.7 times 4 to the third power. And again, the opposite of -2 is +2, plus 1 is 3. And then plus 1.5, and this would be 2.7 times 64, right? 4 cubed is 64, then times 1.5. I'm just going to go back to the Desmos site here and just make a table for this function. And you see when when x is -2, the output is 174.3. Right. Yeah. So 174.3, and no need to round to 4 decimal places there. It's going to just that 10th spot. So this is equal to 174.3. There you go. Right. When the input is -2. Great. All right, so here's another one. So again, f of x equals -3/2 or -1.5 times 3 to the -x power. Again, your base is some positive exponent, some positive number other than 1, and your exponent has a variable in it, right, to the first power. And then you got this plus 3/2 or plus 1.5 afterwards again. So just like the previous example, the horizontal asymptote for this function would be at y equals 3/2 or y equals 1.5 instead of the x-axis. And we're asked to find the value of what's f of 2. So just replace x with 2 here. We have -3/2 times 3 to the -2 power, right? Plus 3/2. And here we have -3/2 then times, now remember 3 to the -2 would be 1 over 3 to the 2, or 1 over 9. And then plus 3/2. Now I can probably do this by hand. You notice that both of these have 3/2 in common. So I pull 3/2 out, and then you'd have -1/9 plus 1 left over. And that would be 8/9. 1 minus 1/9 is 8/9. So 3/2 times 8/9. 2 goes into 8 4 times, 3 goes into 9 3 times. This is just 4/3, or 1.3 repeating, 1 and 1/3. Which, if you're since that goes out beyond 4 decimal places, if you were to round that to 4 decimal places, it would just be 1.3333. Because the next digit would be a 3, so you wouldn't round that up. You just keep it as 1.3333. All right. Great. And again, you can enter that into a calculator if you wish, and you get the same result. All right. So now my last couple of examples involve a word problem from the text that I wrote out. So let's take a look at that. So here it says, for each year t, so years are represented by t, the population of a forest of trees is represented by this function. So again, it's an exponential function, some number times a numerical base to a variable power. A of t equals 115 times 1.025 to the t. So this A of t, A represents the amount of trees in the forest. T represents the time, right, the number of years. In a neighboring forest, the population of the same type of tree is represented by this function. So B of t, B represents the number of trees, equals 82 times 1.029 to the t. And t is time in years again. Round answers to the nearest whole number, right, because we're talking about numbers of trees here, so don't want to count fractions of trees. So I mean, if you think about this, the base tells you, and we'll get more into exponential growth and exponential decay in a future video, but see how the base here is 1.025? So, and then to the t power. This means every time I increase t by 1, the output's going to get multiplied by 1.025. That means there's an increase every year. The number of trees increases by 2.5%. Right? This is 2.5% more than 1. This exponential function, though, for the neighboring forest has a base of 1.029. So each year, the number of trees increases by 2.9%, right? This is 2.9% more than 1.029. So the number of trees in this forest is increasing by a greater percentage each year than this forest. So even though the forest for A, forest A has more trees initially, 115, than forest B has only 82 trees initially. We'll get to that in a second, but eventually, the number of trees in forest B will overtake the number of trees in forest A because the increase is larger, 2.9% every year as opposed to 2.5%. But that's neither here nor there. Let's just answer the questions. So which forest had a greater number of trees initially? Now, when they say initially, that means, t equals 0, right? In the 0th year, right? The initial time. So what's A of 0? That would be 115 times 1.025 to the 0 power. And again, you may recall this. I'm assuming you do know some properties of exponents. A base that's not 0 to the 0 power is 1. So this is just 115 trees. Right, so the forest A has 115 trees initially, and forest B, right, this neighboring forest, has 82. You'll see, right? B of 0 is 82 times 1.029 to the 0, and again, a non-zero base to the 0 power is 1. Right, so this is 82 times 1, or 82 trees. Right. So it looks like, I'll say forest A had more trees initially. Right. Right, and then example 7, related to the same thing, the same question, same forests. Assuming the population growth models continue to represent the growth of the forest, right? So these models continue to represent the growth of the forest throughout time. Which forest will have a greater number of trees after 100 years, right? So initially was t equals 0. 100 years is, t equals 100, right? They told us t represents the time in years. So what is the amount of trees in forest A, after 100 years? What's A of 100? So that's 115 times 1.025 to the 100th power. And we're going to round this to the nearest whole number. All right, so again, I'm going to go to a calculator here. Let's get rid of this stuff from previous examples. And I'll just enter that calculation, 115. All right, 115, oops, 115 times 1.025 raised to the 100th power. And then to the nearest whole number, that's 1,359 trees. All right, so after 100 years, Forest A, if that growth continued, if that growth rate continued for 100 years, the Forest A would have approximately 1,359 trees. And then Forest B, again, if the same model for Forest B continued to model the growth rate, would be 82 times 1.029 to the 100th power. And we'll see what that is. So back to my calculator, just right underneath it, new slot, 82 times 1.029 raised to the 100th power. And rounding that to the nearest whole number is 1,430 trees. So yeah, Forest A, Forest A initially had more trees at time 0, but because the growth rate, right, the 1.029, growing 2.9% a year as opposed to 2.5% a year, the growth rate for Forest B was larger. So eventually, if that growth rate continued, like they're saying, Forest B would have more trees eventually, and we're seeing that here, right? So Forest B has more trees after 100 years. And that's it. That is all we're asked to do, just evaluating some functions, just like examples 1 through 5 in this video. And that is all I have for you as well. That's the last example. And I'm hoping that watching me go through these 7 examples here helps you in some way, when you're asked to simply evaluate an exponential function on your own. And thank you very much for watching.